Hello students, hope you are all well. So already I have discussed effect of nucleophile in nucleophilic substitution reaction. So I have discussed the term nucleophilicity and how it differs from basicity. And sometimes basicity and nucleophilicity uh, are similar, but in some cases both contradict with each other. But right now I am going to discuss about Leavinggroup in nucleophilic substitution reaction. The Leavinggroup in a substrate is also called nucleofuge. It is also called nucleofuge. Okay, Leavinggroup is also called nucleofuge. The ability of nucleophage or Leavinggroup to leave the substrate in a reaction is called nucleofugality, or sometimes it is called nucleofugacity. Clear? And altering the Leavinggroup, if we alter the uh, Leavinggroup, that is the changing of nucleofugality of nucleofuge, will alter the rate of both SN1 and SN2, because in both SN1 and SN2 reactions, bond breaking, as breaking the bond to the two nucleofuge or Leavinggroup, is involved in the slow rate determining step. Just recall the SN2 reaction, which is a single step reaction. Nucleophile attacks the positive electrophilic center, C. Here X is Leavinggroup. So this is RDS, rate determining step. So in the rate determining step, the bond breaking to the Leavinggroup is involved. In SN2, actually it is a single step reaction. Okay, so obviously bond breaking to the Leavinggroup is involved in this rate determining step. So Leavinggroup depends. So the reaction rate of SN2 reaction depends on Leavinggroup. In SN1 reaction, let's see what happens in SN1 reaction. In SN1 reaction, it also depends on Leavinggroup, because the formation of Leavinggroup, that is the formation of cation, which is the rate determining step. So that is why in SN1 reaction is also dependent on Leavinggroup. Okay, let's see. R3CX, departure of Leavinggroup. Okay, then we are getting carbocation. So this is Leavinggroup. Okay, and this is the RDS. Now nucleophile attacks the carbocation. Ultimately, we will get R3C nucleophile. So that is why in case of both, in SN1 and SN2, is both are dependent on Leavinggroup. Now I need to give you a proper definition of Leavinggroup. That is, a Leavinggroup is an atom or group of atoms that is displaced as stable species, taking with it the bonding electron. See, it differs from the substrate as a stable species by taking up this bonded electron pair. Okay. So Leavinggroup differs with the pair of electron. Obviously, a better Leavinggroup is the one which is stable or a poor base. Why I am saying it should be poor base? That is very important. Consider RL, where L stands for Leavinggroup. Okay. L differs from the system, from the substrate RL. Now we are getting R plus and L minus. This is Leavinggroup. So this process is feasible. This process becomes feasible when L minus is stable. Now why I am saying that L should be more stable, or it should be poor base. This reaction is feasible, this process is feasible when it is when L minus is very much stable, and when L minus is very much stable, then it should be poor base. Like stable anions are poor base because they don't want to react with H plus because they are already stable. Then why they are going to react with H plus? That is why stable anions are poor base or better Leavinggroup. So first criteria for better Leavinggroup is that poor base or stable anions. Okay, and we must also consider the strength of this bond, CX or Cl carbon Leavinggroup bond. Okay, a weaker bond would imply a better Leavinggroup because it involves bond breaking. If bond is weak, then the bond breaking will be very easy. That is why iodide ion among the all halides is a good Leavinggroup because of its bulkier size of the negative charge is dispersed and thus stabilized. And also Ci bond is weaker among all carbon halide bond. Okay, Ci bond weaker, this bond is very weak, and I minus is very stable one. Very stable means poor base. Okay, and why it is poor base and very stable? Because it iodine is the size of iron is large, so we have one unit negative charge is present on a large species, so negative charge density is very low, and if when charge density is low, then it should be stable. Okay, so that is why I minus is better Leavinggroup than Br minus, than Cl minus, than F minus. Okay, and on moving from top to bottom in group 17, and means halogen elements, fluorine, chlorine, bromine, iodine, on moving from top to bottom, size increases. Okay, so iodine is the largest one. That is why I minus is most stable among the all halides. I'm going to give you a beautiful examples. Okay, this is HO minus reacts with RCl, alkyl chloride. Okay, aqueous alkali. This reaction is slow. Okay, product is alcohol and Cl minus. Suppose rate of this reaction is, this is rate 1. Similarly, HO minus, RCl, aqueous alkali. Here additionally we have given iodide. This reaction is very fast. And we are getting same ROH and Cl minus. Suppose here rate 2. It has been observed that rate 2 is greater than rate 1. Why? I need to give you a proper explanation. Here, in presence of I minus, the reaction follows the following pathway. I minus is a good nucleophile. Just recall my previous video, okay, where I have explained the nucleophilicity. So I minus is a good nucleophile. Now we have RCl. Now as I minus is good leaving group, good nucleophile, so this reaction occurs at a faster rate. Okay, reaction proceeds to SN2 Ri plus Cl minus, and here also this I minus Ci bond Ri bond is very weak among the all halide. Clear? And I minus is also very good leaving group. Now we have HO minus because reaction is in alkali medium, aqueous alkali. So now again a SN2 reaction, and I minus is a very good leaving group. Just now we have seen good leaving group. Okay, now that is why we are getting ROH and I minus. Okay, so in the second case, this reaction involves two process, two SN2 reaction. This reaction involves one SN2 reaction, but still rate 2 is greater than that of rate 1, because both in the second example both steps are fast. In first case I minus is good nucleophile. In the second step I minus is a good leaving group. So both condition prefers this reaction. Okay, now an approximate energy profile diagram for the reaction makes you better understand. Energy, this is reaction coordinate. In the first case only we have given aqueous alkali, okay, where HO minus acts as nucleophile, only HO minus acts as nucleophile. Transition state, product, reactant. Okay, in the second case reactants is same, okay, but it proceeds through two consecutive steps. First step, I minus acts as nucleophile, and which is very good nucleophile. That is why activation energy is smaller than that of first one. In the second case, in the second step, I minus is good leaving group. Okay. Then also I minus is a good leaving group. So that is why reaction is faster. So red curve is in presence of I minus and blue one is in absence of I minus. Clear? So that is why here I minus ultimately accelerates the reaction. So you can consider that I minus acts as a catalyst. Okay, because it lowers the activation energy. See, it lowers the activation energy than that of previous one. Means absent reaction without I minus. Is that clear? I think it is clear. Now I am going to give you some anions of oxyacids which are very highly stabilized through resonance. As anions of some oxyacid are highly stabilized through resonance, so these anions are actually very stable and they are considered as poor base. Means they are very good leaving group. Again, I am saying, try to remember that poor bases are very stable, and as anions which are very much stable, those are poor base and those are very good Leavinggroup. Okay, and that is so this concept is very important while solving the MCQ. In the in the MCQ, there will be lots of anion, four or five anions. You need to arrange in decreasing or um, increasing order of nucleophilic. Okay, or means which one is better Leavinggroup. Accordingly, you need to arrange. Now, I am going to give you some such oxyanions which are very much stable and they are considered as a poor base. Triflate. This is triflate. See here, CF3 group, 3 fluorines. Fluorine has minus I effect. So anions are stabilized by minus I group, CF3, and electron withdrawing S double bond O. So this is very stable. These anions is called triflate or OTF. Next example is tosylate. This is another important Leavinggroup. This is also very stable. Due to presence of 2 S double bond O electron withdrawing group. So this is very poor base, means good Leavinggroup. Mesylate. OMS. In a similar way, this oxyanions is very stable due to presence of 2 S double bond O electron withdrawing group. We know anions are stabilized by electron withdrawing group or minus I group. Okay, so this kind of anions are considered as good Leavinggroup, and they are also poor base because poor bases are good Leavinggroup. Now I think it is clear. Okay, so in my next video I'll discuss effect of solvent in nucleophilic substitution reaction. Okay, bye.